from wood, which was the original option. So when we go for e to the power half divided by rho, we took these two values in these two columns and created these selections and selected wood. Now, if we have to go for calculating the new material index based on the values of phi max that take into account shape factors, we compute a number of material indices that include the shape factor. Give it a try on your own, and you will come up with the fact that now our choice changed from wood to aluminum. It turns out that steel gets better just because of the fact that phi max is much better than wood. And wood actually turns out to be the worst choice in this particular case once you start making a combination of material properties and shape into consideration. For the same shape, wood is best, but if you're free to choose whatever shape that might work well for the particular design constraint, the AL6061 alloy turns out to be best. Steel just does a little bit better than wood compared to the previous case because it has such a high shape efficiency factor. So the design solution, when you look at this, you basically want to now look at the fact that mass of the new material relative to the reference shape, let's say 1020 stainless steel. Suppose its mass was 1. Aluminum, if you take into account the shape factor, would be 0.15, GFRP would be 0.16, oak would be 0.35. So aluminum would be the best choice. There are some assumptions within those estimates. Think about whether you agree with that analysis or not. Which brings us to the question of how do these theoretical limits for shape factors get estimated for different materials? It turns out that as a rule of thumb, this maximum shape efficiency factor is proportional to the square root of E over sigma, where E is the modulus and sigma is the failure strength. Take a look at these four materials: steel, aluminum, glass fiber reinforced plastic or carbon fiber reinforced plastic, and unreinforced polymers. Roughly, E and sigma values vary in this manner. Accordingly, by using this equation, you can estimate the fact that maximum shape efficiency factor decreases as you go from steel to reinforced polymers. That's the theoretical limit. In practice, empirically, the measured values end up being these numbers. So they are off for sure. But the trends you see between relative values of shape factors, they remain consistent in terms of the rankings of these materials based on shape factors, whether it's based on the theoretical limit or empirical maximum. So, revisiting the problem where you have an original mass, which is given by this equation, and now you have a shape mass of the same material. So rho and sigma are the same geometry, so L is the same, and in terms of the span length, and the bending moment remains the same, you end up having a situation where the mass of the shaped material is reduced from the original mass by this term over here, phi to the power 2 raised 2 divided phi to the power 0.67. For a fixed material, shaping at constant bending strength reduces the mass of the component in proportion to phi to the power minus 0.67. That's what the analysis indicates. We have only looked at stiffness limited designs and strength limited designs under bending. It turns out for the tie rod, shape is not affected in improving the performance based on minimum mass considerations. These were the two modifications to material index that we saw for bending. For torsion, in a similar manner, times a new shape factor based on a torsional loading, which is different from based on bending loading. That's why the subscripts are different. That would be the modification. It turns out that in a analogous manner, the shape factor comes into play for torsion as well, with a modified shape efficiency factor for torsional loading. Similarly, for a compressive loading for a column, you have this modification. Tie, beam, torsion bar, and column. These were the different changes. Let's take a look at a broader range of materials and look at the differences between the shape factors for stiffness limited design and a strength limited design based on empirical values. These limited are set by manufacturing constraints and local buckling. So to go ahead, these were the differences for various shape factors for various materials. To recap, we shall go from here to microstructural shape factors, where you have at these different length scales a number of different structural features embedded in a macro scale shape. Nature takes great advantage of these multi-scale shape factors. For instance, how a sponge is able to, or a coral is able to survive in the ocean, how a palm tree is able to take an amazing amount of load, different kinds of bones depending upon whether it's from a fish or whether it's from a human being. These are all some kinds of possibilities. Here's the stalk of a plant. In the next class, we'll build out from here and go take a look at design exercise 4 next week. There will be a quiz before that. I will talk to you then.